Hello, hello. We are finishing up chapter 13 today. Now, usually when there's sections in the book that are about problem solving, which we see sections B and D are, and actually C is as well. Usually when we have those, I just say, hey, there's going to be a lot of word problems. You need to be able to read them and interpret them and figure them out. They're all going to be different, so I'm not going to really show you any examples of them. And that's still largely true here today. However, there are some particular bits of geometry and other explanations that I do want to go through. So let's just take a look at these three sections together, shall we? So section B primarily is this about like more complicated pictures. So hopefully these steps are pretty obvious to you. Step one, we're going to try to draw a diagram. So we really need to have a picture. Often that'll be given to you, but maybe not always. Within that picture, we want to figure out what is the unknown that we're trying to work out. It's either going to be an angle or a side, as we saw in the last video, how to calculate both of those. The textbook says they usually use x for a side length and theta for an angle, but you know, use whatever variables you like. I don't really care. Step three, we're going to look for the right triangle somewhere in the picture. For right now, we need to deal with right triangles. Later on, we can actually do trigonometry in non-right triangles, but not quite yet. And then once we've got that right triangle, then we can write an equation using a trigonometric ratio. We can solve the equation, and then we've got our answer. So far, so good. Here's some stuff that, we're going to want to keep in mind, though. Okay, we've seen this before. When we have an isosceles triangle, if we draw in an altitude from the vertex angle, or what they're calling the apex, we're going to get two right triangles, two congruent right triangles, in fact. Okay, just something to keep in mind. With circles and radii and chords and all that, remember that when we have a radius that bisects a chord, it's going to intersect it at right angles. So that's going to create two congruent right triangles here and here. And remember, it's the chord that gets bisected. It's not the radius that's bisected. Yes, there's a little, we could continue this radius out, but it's certainly not true that those two side lengths are congruent. They are not. Well, they could be in a very special case, I guess, but generally speaking, they're not. Third, over here, when we have a radius and it intersects a tangent line, so it's when the radius goes to the point of tangency, they're going to intersect at right angles. So we're going to have a right triangle there. Down at the bottom, you might have seen the words angle of elevation and depression. So all that those mean are, if it's an angle of elevation, we're looking from a horizontal line going up. If it's an angle of depression, we're going from a horizontal line going down. It's got to be from a horizontal. Okay? Don't draw something like that and say that that's the angle of elevation. It's not. That's the angle of elevation. Okay? Now, the astute among you may notice that it really doesn't matter whether you're going up or down. So you can actually draw your picture wrong and still get a right answer, because if we have two horizontal lines, looking down here, two horizontal lines are going to be parallel to each other. Therefore, the angle of elevation must be congruent to the angle of depression, because they're alternate interior angles for two parallel lines cut by a transversal. So you could draw your picture upside down. You might have something ridiculous like a tree growing downwards from the sky or something like that, but the math will all still work out, as long as you remember that an angle of depression or elevation need to be drawn from a horizontal line. All right? Now the rest of section B is just word problems and geometry problems that use, for the most part, the things that we just covered. So I'm not going to show you any examples of those because everyone's going to have its own little trick, but We've seen the basics of it. Now we're going to go to section C, which is about true bearings. Section C is just going to be about word problems that have to do with essentially maps and directions. So what is a true bearing? Or I mean, we can just call it a bearing. We don't need to call it a true bearing. There's not like there's a false bearing or something like that. A bearing is just if we think about starting off looking north and then consider the angle of rotation clockwise to get to wherever we want to go, that would give us the bearing to that point. So for example here, let's say we're starting at point A and we want to get to point B. What direction do we need to go? Well, you might look at that on a map and say, oh, we're going northeast, kind of generally. Well, what angle exactly? So we consider looking due north, and then we rotate clockwise until we hit the line connecting A to B. That angle is 72 degrees, so we would say then that the bearing from A to B is 72 degrees, or we could say the bearing of B from A. That's the way they phrase it right here. Anything that gives us a sense of direction, that we're starting at A and going to B, right? It's 72 degrees. And I've never seen this notation before, 72 degrees capital T, meaning true. I've never seen that. But the way that we tend to write bearings specifically is with 3 digits. Kind of throwing it out, the 3 digits kind of tells you that this is a bearing. We are starting this measurement from due north. So we see that down here in the first note. The reason I made a big deal just a moment ago about the phrasing of it, I mean, 72 or 072 is the bearing from A to B. It's because that's certainly not the same as the bearing from B to A, because for that we'd start off at B, looking due north, and again we go clockwise all the way to there, and we say, well, what's that angle going to be? So in this case, that's 252 degrees. And you might notice that the difference between the two, the difference between 252 minus 72 is 180, and that's always going to be true. And you could think about that since the lines going up to north are both parallel. That means that 72 and this angle here are going to be same side interior angles. So they need to add up to 180 degrees. So that's going to make this one here 108, which means if we subtract the 108 from 360, we're going to get 252. Seen more generally, we have two parallel lines. We've got an angle here. That means this angle has to be 180 minus that original angle, which means that this angle here needs to be 360 minus 180 minus x, which is going to give us 180 plus x. And that's exactly what we saw in the previous case. And that's all I have to say about section C. It's just going to be a whole bunch of word problems that have to do with getting from one point to another and figuring out what bearings to follow. Section D, yeah, I got really nothing to say here. We're going to see right triangles in 3D figures. Here's a lovely picture that I've drawn. We've seen problems like this before with pyramids and stuff, right? So we know we can use Pythagorean theorem to figure out some missing side lengths, but now we can also do more complicated ones where we're going to use trig ratios to figure out some missing sides or angles. These 3 sections are all word problems or more complicated geometrical constructions of various types. So we just gotta get in there, get our feet wet, get our hands dirty, whatever type of metaphor you want to go with, and you know, figure them out one at a time, because they're all gonna be different. You knew I was gonna say that.